Okay, good morning everyone. So I hope you all are doing well, although I can see only two participants, one is Reena and other is Varsha up to now. So okay, so I don't think so that you have any doubts from your previous class. So if you have any doubts from the previous class, we can continue. So in the last lecture, last 4 lectures, we did everything about parabolic equations. We understood what is partial derivative differential equations, what are the classification of partial differential equation. We did 3 classifications of partial differential equations, that partial equations that can be classified into 3 categories: elliptic equations, parabolic equations and hyperbolic equations. Parabolic equations, we did everything in detail in the last classes. We did finite difference method to solve parabolic equations. Then we find out the numerical solution with the help of some examples. Also we did the consistency, whether numerical scheme is consistent, whether it is stable and it is convergent or not. We also considered the discretization's error when we say that our numerical scheme or numerical solution converge to the exact solution. So all this part we have done in yesterday's class. So the whole class, whole of the day was devoted to parabolic equations. So today we are going to do elliptic equations. So we will start with elliptic equations. So what are elliptic equations? They arise in steady state problems. Steady state problems means the problems where we don't have the time factor. So those problems are called steady state problems. So elliptic equations deal with such kind of problems and they arise in calculus of variation. Where we deal with the problems of minimizing or maximizing the integral which deal with the energy of the system. So elliptic equations have very relevance in real life problems also. So what are the main elliptic equation? One is Poisson equation, which we also talked in the yesterday's class, just I have introduced, which is Laplacian operator u, that means del 2u by del x2 plus del 2u by del y2, that is equal to some function of xy. So this is the most popular form of the elliptic equation, which is Poisson equation. The other equation we have is Laplace equation. Laplace equation is Laplacian operator and right hand side term is 0. So in the first half of the class we will be going to find out the solution of these both of the kind of problems. Poisson equation when right hand side function is non-zero and when right hand side function is 0. So Laplace equation, we will be finding the solution of these problems. So what are the applications of these problems? These Poisson equation has applications in incompressible. So when we are dealing with incompressible fluid, then we have the Poisson equation occurs, and Laplace equation has application in potential problems, in electricity, etc. So these are some applications of these two kind of problems, and so what we are going to do here is, as you can see here, that equation depend on x, y. So we may be given some domain, roughly I am telling you, although I will be doing that thing in detail also. So we are given x and y, so we may be given some domain in xy plane. This is x axis, this is y axis. So, we may be given some domain and your function may be defined on the boundary points, and we will be taking some grid points, and your solution is known here. So, I have to find out solution at all these node points. So, see, if I am taking particularly this domain, so we have here 8 unknown points where I have to find out the solution. So, you see that we will get here a large system of equations. We will have here system of equations with 8 unknowns. So, it can be little tricky and it can be little lengthy also, that how to solve elliptic kind of equations. Okay, so let us start doing finite difference method for this. So, let us start with Poisson equation first. Let me write down the statement of the complete problem. With the help of this discretization, I will also try to find out the solution of Laplace equation. There nothing, only I have to do the change that I will put here f is equal to 0. So, this is the only change I have to do. Okay, so, let us assume here that this problem is defined over the domain D, where domain D is where x lies between 0 to a and your y lies between 0 to b. So, your x variable is varying from 0 to a and y variable is varying from 0 to b. So, this is our domain here, and let us take the boundary conditions as u equal to u naught is a fixed constant when your x is 0, y is 0 and y is equal to b. Okay, so, this is given to us. Let me draw here this problem statement here. Okay. So, we are given here x and y. So, this is your x axis, this is your y axis, and this I am taking here 0 to a. So, suppose this is a and y is from 0 to b. So, this is b here and this is our domain here. So, what is given to us here? We are given here that function value is u naught, which is fixed at x is equal to 0. So, here x equal to your x is equal to 0 here, this here function value is given to us, which is u naught. When y is equal to 0, this is also again given to be a constant, which is u naught. So, here when y is equal to 0, this is again given to be u naught, and y is equal to b, it means here also we are given function's value to be u naught. So, on this domain 3 conditions are given to us, and what about the fourth? Let me write down that here. So, because I have here 4 borders of this domain, so I should have one more condition here. So, that is del u by del x, that is equal to alpha u plus beta at x is equal to a. So, here we are not given function's value when x is equal to a, instead of that we are given this condition, and we know that this condition, which is a combination of u and its derivative, is a kind of Newman condition, and we will see that how to solve this kind of condition. Okay. So, this is the statement problem where we are given boundary conditions, and let us see how further we are going to solve that. So, when we are doing finite difference method, so we know that our domain we have to divide that into uniform grid points. So, what I will do here is, let us total length in x direction is a, and let me take here delta x as a by m. I am dividing this whole length into m equal parts, and this is my step size or grid size here. Similarly, delta y, this length I am taking to be b, and let us divide that into n equal parts. So, I will have here n points. So, what will be the points here look like? Let me write down this thing here. On x axis, this is a, this is 0. So, this first point will be x naught. What will be x1? x1 will be nothing, just delta x, and x2 that will be 2 delta x, and similarly last point is your xm, which is here xm, which is m times delta x. Similarly, I can write down this, I can take a uniform partition of this, which is y variable, and what will be in the y direction here? You are taking here 0, which is y naught, next point will be y1, which is nothing, just delta y here, and then we have y2, which is 2 times delta y here. Similarly, I can write down the other points. So, first thing, in finite difference method, your domain is given to you, you have to do a partition, that can be uniform, that can be non-uniform, but first we are dealing with the uniform partition. So, I am taking here m equal parts, in the y direction I am taking here n equal parts. So, we have taken first uniform partition, then we will start doing here finite difference method. Okay. So, now okay, I will erase some of the part and let us see how we can do this further. Okay, so let me write down here points xi's. Xi's are nothing, just I times delta x, and your yj notation I am going to give for y coordinates. So, this is j times delta y. So, you are given here xi's and yj. So, what we do here in finite difference method, you know that I will discretize the problem at a particular point. Let us take the point as xi yj. So, I am going to consider the problem is discretized version, where I am going to consider that at the point xi yj. So, this should be here y, yeah. So, this is our y here, fine. So, I am going to write down this here and I will apply here central difference formula for second order derivative. We have done here the derivation in the last, yesterday we have done the derivation for second order derivative also. So, now just check the formula for this or representation for this. What I can write down here? I can write down here ui plus 1 j minus 2 ui j plus ui minus 1 j divided by delta x square. So, because we are given here two variables x and y, so we are taking first derivative with respect to x, your y coordinate is going to be fixed. So, that is why y is represented by j, and I am doing here central formula in the x variable. Similarly, I am going to write down the same thing for this second order derivative here in y. So, you should get idea how I am going to write down this. I will take here ui j plus 1 minus 2 ui j plus ui j minus 1 divided by delta y square. So, both of the places I am applying here central difference formula. You know that central difference formula is a method of order 2. So, and right hand side, what can I write down for right hand side? I can write down y fij. Fij is nothing, just function's value at xi yj. Further, if you want to write down here the truncation error or term, what will be that term? You can write down this as delta x square plus order of delta y square. So, we have this term here. So, further we are going to simplify that. In the questions or problems, you may be given delta x is different from delta y, but I want to derive a simplified form. So, let us assume here that your delta x is same as delta y, and for simplification I am giving that as name h. So, that I will put here both of the terms as h. So, let us put that value here. So, I am going to put here h square, and I am going to neglect here the truncation error. So, further how I can write down this? I can write down this as, okay, so directly I will try to write down the scheme, check it whether this is fine. Uij, that is equal to, this is h square, both of the term will go on the other side, h square fij. This is 4 times uij, which I am taking on the other side and then divide by 4. So, what I will get here is 1 by 4 what should I write down here? ui plus 1j plus ui minus 1j plus uij plus 1 plus uij minus 1, and here we will have minus 4 times f 4 times, or okay, this is minus h square times fij. Yeah, so this is our formula here. So what I am doing here is I am taking this term, combining this term and taking this term on the other side and other terms on the other time. So this is our final numerical scheme. So this is our final numerical scheme, and whenever we are writing numerical scheme, you should be clear that what is the value of I and j. So just check what is our discretization points here and what should be the value of I and j. I means our x direction. I am taking here m equal parts. Here value is given. Here when x is equal to 0, value is given. When x is equal to given, here this value is not given to us. So I have to, if first point is x0, next is x1 and last one is xm. I am given here functions value at x0, but I am not given functions value at x1 up to xm. So what I am going to write down here? I will write down here your value of I lies between 1 to m. Okay, so what can we write down about j here? J, when your y0 is given here, that value is a constant. Yn is also given here, that value is a constant. So that values we know. So clearly your j will lie between 1 to n minus 1. So we can say that this is our numerical scheme. Values of I and m are given to you. Okay, so next let me first draw here the stencil of this problem, how stencil of this problem will look like, just like we were doing in previous classes, that how to write down the stencil of the scheme. So what can we write down here? Let's check here. Okay, so this is here I minus 1, I plus 1. Let's take this time level as here, this one as j minus 1, this as j, and this as j plus 1. Because in the scheme we are getting j as well as j plus 1 and j minus 1, I minus 1 and I plus 1. So I need all these points here. Okay, so in this scheme, so uij, so uij means this point, okay, which is given to be here, our right hand side term. What is ui plus 1j? Is this point. Ui minus 1j is this point, and here ui j plus 1 and ui j minus 1. So this is ui j minus 1 and this will be ui j plus 1. So up to here, if you have any doubts or in between wherever you have doubts, you can write down in the chat box. I can take your doubts here. Okay, so this is our stencil here. So this is called standard 5-point formula. 5-point formula because this point we are involving here total 5 points and this point is depending on all these points. So what can I write down here? If we talk about Laplace equation here and your f function is 0, so clearly your uij is depending on all these 4 points. So that formula is called standard formula, standard 5-point formula. And what should I write down? Uij is 1 by 4 times of this, 1 by 4 times of this point, 1 by 4 point of this, 1 by 4 times of this point. So this is our standard 5-point formula which we can apply here and we can find out the value of uij. Okay, so what we are going to do here, we will be doing here two kind of problems, Poisson equation as well as Laplace equation. Let me tell you one more idea. So what will your problem become here? If your f is not given here, this term will be 0 and this remaining formula is called standard 5-point formula. Standard 5-point formula. and with the help of this I am going to derive one more formula. I actually not deriving, I will just tell you how we can write down that other formula, and we will be doing one question based on that also. So, this is our formula where this point depends on all these 4 points, fine. Now, when we do Laplace equation, which is ux x plus u y y that is equal to 0. Here this problem is invariant when we rotate our axis about 45-degree angle. So, we know that this is your 45 angle. So, this is our 5-point formula. If I rotate the problem here, this whole stencil at the angle of 45. So, what will happen to that if I rotate that at 45? Let me draw that here. Okay, so what I will get here? You just first think with the help of a diagram, then we will be writing that formula here also. Okay, so this is the point. This is the whole diagram. I want to rotate this whole diagram at the angle 45 because that remains invariant. So, what I will get here, whether it is okay if I write down all these 5 points. This point will transfer to here, this point will transfer to here, this one will transfer to this one will be rotated to this one. So, I have here these 5 points. So, this is our standard 5-point formula that we use in questions. Side by side we also use this 5-point formula, and you can see that this is actually diagonals here. So, when I am applying this approach, that is called diagonal 5-point formula. So, this is our diagonal 5-point formula. So, in some questions we may use these both of the things. So, let us first moving to the next method. I will explain this idea with the help of one example, because I am going to deal here, I am going to give you idea about 5 different methods. So, 2 are here, which is a standard 5-point formula or diagonal 5-point formula. Let us do this first, then we will move to the other methods, fine. Okay. Okay, so let me go to this example. Okay, I want to mention you that these of the numerical examples are done with the help of my research student Varsha, who is online. So, I want to say thank to her for preparing these examples for me. Okay, so let us move to this problem here. So, we will deal here with the Laplace equation, which we are writing here Laplace equation uxx plus uyy that is equal to 0. Boundary conditions are given here 0, and when your y is 0, function is 0, when your x is 0, your function is 0, and when your x is 1, it is given 10x, and y is your x is 1, then it is given 20y. What does that mean? So, what I am doing here is I am taking h equal to 0.25. H is equal to 0.25 means I am taking 1/4 as step size. So, it is clear that your first point will be x is equal to 0, next will be x is equal to 0.4, this is 0.25 means 1/4, and we will have here total 5 points. The same for simplification we are taking here the same step size in y direction. So, here also we are taking those points, this y is equal to 0, 0.25, 0.5, 0.75 and up to so on. Now, when x is equal to 0 and y is equal to 0, the function value is given to be 0. So, you can see here that when x is equal to 0, so function value is given to be here 0, all these values are 0, and here also function value is 0. So, this boundary, 2 boundaries I know what is this value. So, when fx1 is given to be 10x, let us think about this. when your y is 1. So, this is 10x. So, here your x is here at this point, your x is 0.25. So, it is 10x. So, I am multiplying that distance here with 10. So, next point is 0.5, I am multiplying that with 5, and here 0.75 with 10, and here we are getting 10. Similarly, I can get here the other boundary points. So, this is our whole grid where I am aware about the value of the function at all the boundary points. So, only points that are unknown to me are these 9 points which are given here in between. So, these 9 points we have to find out with the help of finite difference method. So, what we will be doing here is just try to understand what I am going to do here. Okay, so first I will start with this point which is u22. So, here we have two approaches. This is our standard formula where this point can be find out with the help of this 4 other points, which is standard formula, and this point can be find out with the help of the diagonal points. So, this is our diagonal 5-point formula. So, we have to understand here that what is already given in the problem to us. So, you know that if I am doing this, I can also apply here this standard diagonal formula. So, this point will be 1 by 4 times of this 4 diagonal points. Okay, that is what I am writing here in the next slide. So, u22 is the average of all these 4 points, so which I get as 2.5. Then I move to u13. u13 means this point. So, if I apply here standard 5-point formula, I will get here this as a form that is a combination of this u23 and u12. These 2 points are unknown to me. I can't find out the value of u13 with the help of these 4 points. So, what I will do again for this u13, I will apply here the standard diagonal 5-point formula. So, what will be u13 here? That will be average of 0, 0, u22 and here this 5. Okay, so that's what I am writing it here. So, similarly, I am going to apply that on u33, that is on u11 and u31. So, in this diagram, after applying our diagonal formula 5 times, I will get all these 5 points. Fine. Now, further 4 unknown points are given to me, and how I will going to find out this 4 different points. So, now let us come to this, that how I am going to find out this point. Suppose this point, this is u21. Now, by the diagram it is very clear to you that I should apply here the standard 5-point formula, because this blue point means u21 can be written as a combination of this point, these 4 points, and all these 4 points are already known to me. So, I will apply here standard 5-point formula. The same thing I can apply for other 3 points, which is u12, u32 and u23. So, I will apply here that formula and I can get here the value of other points. So, total here we have this 9 points were unknown, and we are using a mixture of standard 5-point formula or a diagonal 5-point formula to find out the values of these unknowns. So, by applying this procedure, I will get this formula. Okay, this is one of the approach that we can apply. Now, let us see about the other approaches that I can apply here. Okay, one more thing I have to tell you here. Okay, because this example we have done when your boundary points are given to you. Okay, if it is not given to you, then I have to think about some other approaches, that how we are going to solve that. Okay, so now let us move further and let me tell you the other methods to solve this kind of problem. Up to here, if you have any doubts, you can ask me. Okay, so this is one of the approach. Other approach is we can apply here iteration procedure. Okay, up to now we are not doing any iteration. So what we can do here is the points, this point is depending on this one, fine. So I can apply here iteration procedure. What does that mean? So for iteration procedure, again I am going to apply here three different method. One is Gauss-Jacobi method, other is Gauss-Seidel method, and last one is successive over relaxation method. So let's talk about Gauss-Jacobi method, or you can say just Jacobi method. Okay, so what can we do here? We can do here Uij r plus 1th iteration, that is equal to 1 by 4 times of ui plus 1j plus ui minus 1j and uij plus 1 plus uij minus 1 minus h square fij. Okay. So what I am doing here, that this is r plus 1th iteration, and let me write down here this is rth iteration. Because why we are doing here iteration procedure? Because our grid size is small, you will have here more points that are unknown, and it's more difficult to find out by this standard 5-point formulas. So what we do here, we can apply here because we are given a number of unknowns that is very high. So we can apply here iteration procedure. So iteration procedure, we will try to find out a better and better solution. So what we can do here, I am applying here iteration procedure. We will start with the first iteration or initial iteration. You can assume your initial iteration any number. So suppose I start with first iteration or 0 iteration. If I take here r is equal to 0, so this is my 0 iteration, which I am assuming it's some value I am assuming. When r is equal to 0, I will get here 1. So I will get, with the help of 0 iteration, I will get here the first iteration. Similarly, when I put here r is equal to 1, with the help of first iteration, I will get here the value of the second iteration. So in every equation, I am going to apply on the right hand side rth iteration, and left hand side we can apply here the r plus 1th, and we will find out our solution. This is one of the procedure that we can do here. Okay. Okay. So let's talk about here. For simplification, you can also take your all uij 0 iteration as 0 also you can start. Okay, there is no problem in that. If you are starting with 0, so you are putting that to be 0 here, this will be 0. So uij first iteration will depend totally on your value of h and your right hand side function. So I can put here the value of right hand side function, and we can find out here the value of the next iterations. Okay. Okay, so next is the procedure which is called Gauss-Seidel method. Okay, so what is Gauss-Seidel method? Here what we were doing, in the right hand side I am using just previous iteration, left hand side I am writing the next iteration. Here only some difference is there. What I am going to do here is uij r plus 1, I am going to write down the same thing, and let me tell you what will be the major difference here. 1 by 4 ui plus 1j plus ui minus 1j plus uij plus 1 plus uij minus 1 minus h square fij. So this is our formula here. Now see, uij is here. Suppose I write down here uij. Okay, so what is the previous points here? This point is uij minus 1. This point will be ui minus 1 j minus 1, and this is ui plus 1 j minus 1. So when I am moving to this time level, which is jth time level, I already know the function's value at j minus 1th time level. Okay. So, this value is already known to me. So, I am going to take advantage of that, and when I am going to do this, you can see here this is ij. When I write down I minus 1j, this point is already calculated because this is a previous point, and this is also already calculated. So, because it is already calculated, so I will be writing here I plus 1th iteration, I r plus 1th iteration, and here I will be writing here rth iteration. So, this is the only difference between your Jacobi method and Gauss-Seidel method. Here we are changing all the values, then we are using updating that value, but here immediately I get some value, I use the updated value, and I will get a better solution with the help of the Gauss-Seidel method. Okay. So, let me show you some examples for Gauss-Seidel and Jacobi method. There is one more method, first I will explain this, then I move to that other method also. Okay. So, let us check here other examples. Okay. So, let us check here other example. So, just like I have explained you now Gauss-Seidel, Jacobi method. So, this example contain all the 3 methods. First I will explain 2, then I will go to other method, then I will again come back to this example. So, we are given this problem here, Laplace equation is given to you and your boundary conditions are already given to you. So, here on the boundary here, so this is given to be here 0, 0, 0, 0, this 0, and this value is given to be here 10. So, 4 points are unknown to me which I have to find out. Now, you should ask here a question that why it is not possible to apply here standard 5-point formula or standard diagonal 5-point formula. You see the diagram here. So, you see whether we can apply that diagram, still we are going to get here the unknowns. Okay. So, we will get here, we have here 4 unknown points and we will get here 4 equations in 4 unknowns. So, okay. So, here check this equation here which I am writing here. Yeah. So, uij, that is 1 by 4 times of this value. Okay. So, I am going to apply this formula here. So, here u11, which is this point, okay, this point is the average of, by standard 5-point formula, this will be the average of these 4 points, okay, which I am writing it here in the next line, that u11 is 1 by 4 times of u21 and u12, fine. But I am writing here Seidel method and I am applying here the iteration. So, first thing is I have to check u11 and here it is 21 and 12. So, both 21 and 12 are the points that are unknown to me yet. So, I am applying here the rth iteration here. Then u21, what is u21 from here? This u21. When I move to the point u21, that will be 1 by 4 times of u12, this 0, 0 and u22. So, it is a combination of 4 points in which u11 I have already calculated. So, because I have already calculated u11, so I will write down here r plus 1th iteration and other point, because still it is not calculated. So, I will write down here rth iteration. Similarly, when I move to the next point, which is u12, is this point. This is again average of u11, u22 and 10 and 0. Now, u11 is already calculated. So, for u11 I am using here next iteration, which is r plus 1 iteration, and u22 I am writing here rth iteration. So, this is how we are writing all these equations. Then u22, we are talking about u22. When I move to u22 point, it means this point. This is a combination of the points which we already know. All the 4 points are already known to me. So, what I will do here, see, in the last point we are getting here r plus 1 both, okay, because these 2 points all are already calculated by this previous equation. So, I can use the updated value and I can write down here r plus 1 both of the sides, fine. Now, I will start here with r is equal to 0. For simplification, your 0 iteration you can assume that to be 0, just like I am doing it here, you can assume that to be 0. So, when you put here your rth iteration 0, you put every value here, clearly u1 1 1, that is 0 by putting that value here. u2 1 is 0, u1 2 is 2.5 and u2 2 is 3.125. So, in the next step you can do here for r is equal to 2, r is equal to 1 here. So, when r is equal to 1 we are writing right hand side is your 1 and 2 and left hand side is our second iteration. So, that for that I am going to use all these values which we are calculating here. So, the same procedure I can apply here to find out the value of the iterations. Okay, so this is Gauss-Seidel method, and Gauss-Seidel method is a betterment of the Jacobi method that I am writing here, and in this example we can see that how your Gauss-Seidel method is better than your Gauss-Jacobi method. Okay, so these are the iterations here. If we apply here different iterations, and so we are doing here this first iteration and we are doing this approximately how many times we are going to do this? We are going almost 10 times, and you see that after 10 times we get the solution almost as 1.25, this is almost 1.25, this is 3.75 and this is almost 3.75, almost after applying the iterations 10 times. Now, let us think about the Jacobi method where we do not use the updated values. What we do here, we write down r plus 1th iteration as a combination of your rth iteration. So, there we do not need to worry about just left hand side, everything is r plus 1th iteration and your right hand side is their rth iteration. So, if I assume that my initial iteration is 0 here, you put this 0, clearly this will be 0, this will be 0, this will be 10 by 4 and so this will be 10 by 4. When I put first iteration, this will also be 10 by 4. So, that is what I am getting here, this is 2.5, 2.5 and 0 and 0 for r is equal to 0. So, this I am getting here first iteration. In the next step you will put here r is equal to 1 and we will get further value and we will apply here different iterations to check the values. Let us see that table here. Okay, so this is the table here and see we are doing almost here 15 iterations, and you see after doing 15 iteration we are getting almost 1.25 here, this is almost 1.25, this is almost 3.75 and 3.75 almost. So, this table indicates that your Gauss-Seidel method is more efficient than your Gauss-Jacobi method, because here after 15 iterations we are getting that answer, even not that answer, we are getting approximately 1.25, but by Gauss-Seidel method just by applying 10 iterations I am getting here the almost almost 1.25. okay, here also we are getting all the decimal zeros, so we are getting a better answer. So, this is the way how we can apply iteration procedures to find out the solution of your elliptic problem, and we can apply different iterations, and we should also observe here that the more iterations we are doing, we are going near to the exact solution. Okay. So, here you see that we are approaching to the exact solution. Here after some time your decimal start repeating, it is 1.249, so they will start repeating. Okay. You can see here that how they start repeating here and approaching to 1.25. So, the same we can see here, and this is getting better, fourth decimal place is getting better, and that is also happening for other values of the iterations. Okay. So, this is a difference between these two methods. Now I will tell you about the next method. Okay, so if you have any doubts, you can ask me. Okay, so next we are going to do a very nice method which is called successive over relaxation method. Okay, I need that formula, but okay. Okay, I am not going to erase this everything because I may need this formula. Okay, so this was our Jacobi method, and what was your Seidel method? Seidel method was, here I have r plus 1 and here also I have r plus 1. Okay, so this was the method that we have already done. So next method we are going to do is write down the next method. So that is our successive over relaxation. Successive over relaxation method. So that is sometimes also called SOR method, successive over relaxation factor. So we have a factor here that is called relaxation factor. We will introduce that factor, and the goal of this introducing this method is that we want our solution to be better and we want our solution converge faster than these two methods. Okay, so this method is an advantage over the previous methods, which is Jacobi method and the Seidel method. So what we are going to do here, let's understand that how I will write down the formula. So here what I am going to do here, uij, that is r plus 1, that is equal to, I introduce a factor which is omega here, 1 minus omega I am writing here. So let me first write down here, then I will explain how I am writing this thing. And this is w or omega by 4 ui minus 1j plus ui j plus, this is j minus 1, r plus 1, r plus 1, and plus here ui plus 1j, which is r, and here ui j plus 1, which is here r, minus h square f I j. Okay, so I am writing this form here. So in successive over relaxation method, what we are doing here, we are introducing a constant here which is called relaxation parameter, which is omega I am writing here. Now I am writing a new formula which is our successive over relaxation formula, and how I am writing that, you see here this formula which I am writing here, this formula is nothing, just our Gauss-Seidel method. Okay, so this is our Gauss-Seidel method. So what I am doing here is, I am writing uij r plus 1th iteration as 1 minus omega uij rth iteration and omega times the formula that I was getting with the help of Gauss-Seidel method. Okay, so I am taking a combination of these two values. You can see here, when your omega is 1, what will happen to this formula? If your omega is 1, this will be nothing, just it will become this method. Okay, let me write down here that when omega is 1, your SOR method becomes the Gauss-Seidel method. So that becomes the Gauss-Seidel method. Okay, so we have here three cases when your omega lies between 0 to 1, then this SOR method, we call that this method we have under relaxation, when this omega is less than 1. And if your omega is greater than 1 and less than 2, then we say that this method is over relaxed or over relaxation. Okay, so if your omega is 1, we get the same formula that we have already done, that is Gauss-Seidel method. And when your omega lying between greater than 1, this is over relaxed, and if it is less than 1, that is called under relaxation. So we are going to do our questions with the help of this relaxation method. Although there are also procedure that how to find out this relaxation factor, I will tell you that directly how we can find out that relaxation parameter. So let's check out how we are going to do that. So I think let me write down it here. So one more thing here we should check, that this omega can take any value. So I have to check that value of omega that will give me the better answers. Better answers means you have seen in the previous examples where we are applying Jacobi method and Gauss-Seidel method, and in one example your Gauss-Seidel method converges fast to the solution in comparison with the Gauss-Jacobi method. So our idea of introducing successive over relaxation method is that we converge to the solution very fastly. So we have to find out that value of omega for which we do not need many iterations. In small number of iterations we can converge to the solution very fastly. So we have to find out the optimal value. So write down optimal relaxation factor. Okay. So we are going to find out the optimal relaxation factor for which our solution will converge fastly. So this value is given by, I am not going to do the derivation of this value is given by 2 by 1 plus under root 1 minus rho square. Okay. So this is 2 by 1 plus 1 under root 1 minus rho square, where rho value is given by half of cos pi by m plus cos of pi by n. Okay. So we should ask here that what is capital M and N. When I started doing elliptic equation, I told you that M is the number of subintervals in the x-axis x direction and N is the number of subintervals in the y direction. So your M and N are given to you. For further procedure, we assume that your M is equal to N. If your M is equal to N, what will happen here? This will become 2 times, this 2 will cancel. So that will be simply cos pi by M. Okay. So you can write down that case here also. Let's see here what will happen if your M equal to N. What will happen to M equal to N? If M is equal to N, your rho will become cos pi by M. So this is cos pi by M. When you are going to put it here, 1 minus cos square pi by M, that will become sin square pi by M, square root of that. So what will be this value? This will be here, your optimal value will be 2 by 1 plus sin pi by M. So in any question, whatever number of partitions or subintervals are given to you, that is your M. Choose that value, find out the value of rho, then put it here and put that formula here, and you can find out the optimal value of omega for which you will get a better solution. Okay. So this is your successive over relaxation method. Okay. So if you have any doubts up to here, you can ask me. Okay, so I will take a break of just 2 minutes and I will be back. Then we will be doing some example with the help of successive over relaxation method. So just go through this. I am just coming back in 1-2 minutes. Let's start doing this relaxation over successive over relaxation method and see that how this method work, whether this method is faster than your previous methods. So for that we will be doing here some examples, and so this is the same example that we were doing with the help of other two methods. So let's see here what's happening in this example. So I am here applying the same formula, which is 1 minus omega times of UIJR and omega time your Gauss Seidel formula. So the formula that I have just derived here, so that formula I am writing here. So the same thing I am going to write down here for I equal to 1 to 2 and j is equal to 1 to 2. Okay, because let's recall here the example. Yeah, so here these 4 points were unknown that we need to calculate, which is u11, u21, u12 and u22. So your I is 1, 1, 1 and your j is 1, 2. So these 4 points we will get here. So we are writing this scheme here with the help of this SOR method. So we will get here in this problem, when we are writing this formula here, I will write down here I is equal to 1 to 2 and j is equal to 1 to 2. We will get some formula here. So this is what I am writing it here. So we get a system of these 4 equations in for 4 unknowns. We can start with the 0th iteration, and I am taking here initial iteration as 0. So our all the initial iteration values are 0 here. When I put this value here, I will get the value of your next iteration. So first, if it is 0, it is 0, it is 0, then clearly we can find out here u11 that is equal to 1. So it's up to you that whether you want to find out the optimal value of omega, or directly you want to take some guess, rough guess, and you want to solve the problem. So here we are taking this value of the omega, that is as 1.1, and we will check here that how it works here. So by taking omega as 1.1, see, by just 6 iteration I am getting my solution 1.25, 1.25 and 3.75 and 3.75. So this method is converging just in the 6th step. So definitely this method behaves better than your Jacobi method and Seidel method, because in this other method, you see, in Jacobi method we were doing approximately 15 iteration to get the same answer, and in this Seidel method we were doing that in 10 iterations, and by SOR method we are doing the same thing but in just 6 iteration. So this is the advantage of your SOR method over other 2 methods, which are Jacobi and Gauss-Seidel method. Okay, and actually it's a kind of generalization. If you take omega particular value to be 1, then you will get here Gauss-Seidel method. So Gauss-Seidel method is definitely better than the Jacobi method, but when I am doing here for any other value, we are getting better results and fast convergence. Okay, so here is next table indicates that for different values of omega how our solution converges. So here we are taking different values of omega, omega 1, 1.05, 1.07, 1.8 and 1.1, and you see if we take omega 1, which means what does that mean? If omega is equal to 1, that means our Gauss-Seidel method. So we are getting our solution in 11 iterations. So even if I take omega as 1.08 or if I take 1.1, I will get a solution in just 6 iterations. So you can try different values of omega, you can check that which value of omega is better. Otherwise, you have the formula to find out the optimal value of omega. You can calculate that value of omega with the help of this formula, and you can check the optimal value of omega, for which we will get the solution faster. Okay. Okay, so let's do here one example. In the previous example, we were given here the boundary condition. Okay, let me show you the statement. Our diagram was already given to us and your boundary points are given to you, and this equation was Laplace equation where right hand side function is 0. Now we will do another example which is for Poisson equation. Okay, so I am taking here Poisson equation where right hand side is 8x square y square, and this is our domain 0 to 1, 0 to 1, and h is given to be 1 by 3. So I am taking 3 equal subintervals in x direction as well as in y direction, and we have to okay, and the values of u on the boundary is given to be 0. So everywhere boundary points are 0. You have to apply here Gauss-Seidel method and Gauss-Seidel SOR method to check the value of this one. So we are assuming our, okay, let me draw here this diagram. So this is 0, 1 by 3, 2 by 3, next point is 1 here, and in this direction also we are given this 1 by 3, this is 2 by 3, and okay, and this is 1. So okay, let me take this 1 here and this I am going to erase. So what we get here? We get here, this is our diagram. Okay, so boundary points are already given to us. Okay, so only these points we have to find out. So these points I have to find out, which are 4 points we have to find out. We have to apply Gauss-Seidel method as well as we will apply here SOR method. Let's take because boundary values are given to be 0. So here function value is 0, 0, 0, every value is given to be 0. So this is 0 given to us. By Gauss-Seidel iteration scheme, we can write down this value here. This is 1 by 4 times, which I am writing here this formula. Okay, so this formula we have written here that uij is 1 by 4 times of all these things and h square fij. Okay, here we are using the notation gij. So what is fij here? This is 8 x square y square. So what will be x? Okay, let me write down here. This point is x0, this is x1, this is x2, this is x3. So what is your xi here? Xi point is I times h. What is h? 1 by 3. So and similarly you can write down yj is j times 1 by 3. 1 by 3. Okay, so here we are putting here what is value of f at xi yj, that will be here this I 1 by 3 I am using, j by 3 I am using, so I am putting that value here. Okay. So the same formula I am writing here 4 times by taking different values of ij. We are writing here Gauss-Seidel method, fine. So we get this formula. I am putting here the value of fij function also. So we are putting here this value of fij here. We get here a system of 4 equations in 4 unknowns. Then we have to write down here the iteration procedure and we will try to get here the solution. You can check it here if it's okay with you how we are writing the system, or still you have any doubts. So by taking our initial value to be 0, initial iteration to be 0, what we can find out here? We are getting our solution as this value in by doing 8 iterations. Okay, so we are getting this solution. Let's now further apply a better method, which is SOR method, and check that what we will get here by applying this method here. What we write down here? Omega times, this is Gauss-Seidel method, and 1 minus omega times your Uij. So we will put this formula here, and further it depends on you which value you want to write down here for u omega. Either you want to find out the optimal value or you want to just write down this value. So what we can do here, let's take here again value of omega as 1.1 and we will get the solution in 6 iteration. So we can compare both of the things, that the same solution here by Gauss-Seidel method I am getting in 8 iterations, and Gauss-Seidel SOR method I am getting the same solution in 6 iteration by taking omega is equal to 1.1. Okay, so with the help of with the help of these two methods I can find out the solution, and we can see that we can reduce the number of iterations by taking optimal values of W. Okay, so let's see here further what can we do here. So in all these examples we are taking our boundary condition to be 0. So because boundary condition is given to be 0, so already we are given at boundary condition, we have to find out a few points. So let's just check some other example also. That how to handle the other kind of problems. Okay, so this is done and this is also done. So I will now roughly give you idea that how to deal. Okay, so this is the example done for elliptic problems, and now I will try to give you idea that how to handle the other kind of boundary conditions here. Okay, so let me write down here this case, that what will happen at boundary points if your boundary conditions are not given to you. Okay, so let's take here this condition. Initially I wrote that, but we haven't solved anything. So let's take this condition when we were writing here u equal to u naught at x is equal to 0, y is equal to 0 and y is equal to b, and del u by del x, that is equal to alpha u plus beta at x is equal to a. So if we take this, how we will solve that? Let me write down this thing here. Okay, it means your domain is given like this. It is x is equal to 0, y 0, y b, and this value is already given to me. So this point where your y is equal to 0 and x is equal to 0 and your y is equal to b 0, that is already given to me. Okay, so function value is not given to be here. So this is not given to me. So how your questions will change when this is not given to me? What we will be doing here, I am taking here x points, which is x naught, x1, x2 and here xm. So when I am writing this condition here, okay, I told you that I will be writing here I is equal to 1 to m. M I will be writing because m I do not know that value of u at xm point. Okay, so I am taking that equation at m also. So what I will be doing here, if I put here m, what will happen to this? It will be u m j, it will be here u m plus 1 j. So how to deal with this u m plus 1 j? For that our this boundary condition is going to help us. Okay, let's see what can we do here. This is at x is equal to a. which means where x is equal to xm. So, what I will be doing here is I can apply here central difference formula, and what I will get here, u value at, what can we write down here, u value at m plus 1 j minus u value at m minus 1 j divided by, when I apply here central difference formula, what will happen to the denominator, this will be 2h, and that is equal to alpha u m plus beta. Okay. So, we have this formula here, and because when I write down here I is equal to m, I get m plus 1, that point is actually a fictitious point. Okay, so this is fictitious points because this is going outside our range xm plus 1. So, what we will be doing here, with the help of this boundary condition, I will find out the value of um plus 1. So, what is um plus 1 j? That will be equal to here um minus 1 j plus 2h times alpha um plus here we have beta. So, I am going to use this relation here, and when I put here I is equal to m, I am getting here m plus 1, that I am m plus 1, I am going to utilize this value so that this point is removed, because this is a fictitious point, and we can simplify and we can solve this equation. Okay, so this is the way how we are going to solve this this problem with any kind of boundary condition. It may also be possible that both of the boundary conditions are not given to us. This is also not given to us. So, what we are going to do, then u value at x naught is not given to me. I will write down here I from 0 to m, and if I is from 0, what will happen to this point, that will be u minus 1. It means some condition is given here at x is equal to 0 also. So, again here I will apply central difference formula. I will get here u minus 1 j in terms of the points that I already know. So, using that boundary condition, I will find out this value, put in the scheme, and we will get a system of equation. Okay, so, this is all about elliptic equations, that how to solve elliptic equations. We have done here almost 5 ideas to solve elliptic equation. We have done here iterative schemes and non-iterative schemes to solve elliptic equation. We have done standard 5-point formula, diagonal 5-point formula, and Jacobi method, Seidel method, and SOR method. Okay, so so this is some just idea about the some of the methods how to solve elliptic equations. Although we have limited ourselves to a particular domain, which is rectangular or square domain. If it is some other kind of domain, then we have to deal with that separately. So, that thing that's not a part of the course. Okay, so, but with the help of same idea you can solve this. If in the end of the course I have time, I would like to explain you how to solve elliptic equation if it is given in polar coordinates. So, I will like to give you idea about the elliptic equation in polar coordinates. Okay. So, next let us start doing then the next type of equations, which is hyperbolic equations. Okay, so I hope you remember what was the hyperbolic equation when initially we were doing the classification of the problem. So, let us start writing hyperbolic equations. So, hyperbolic equations we will start. What are hyperbolic equations? They depend on time, they are time dependent, just like we were doing elliptic equation, their time don't appear, so they were not depending on time, but this are depending on time. But they describe the vibration within objects and they also tell how about wave propagation. They also tell us how wave propagates, and that is why they are also called wave equation. And so, let us write down the simplest form of the vibration problem or wave equation. Or you can write down, let us start with some hyperbolic equation that is of vibrating string. If we take a vibrating string, so what will be the wave equation related to that? So, double derivative of u with respect to t, that is equal to double derivative of u with respect to x. You can take here some constant also. If you want that to put that as 1, that is also fine. Some simpler case I can take that to be 1 also, fine. So, let us take this. Let us take the domain of x from 0 to L and t is greater than 0. So, your boundary conditions for simplification I am taking that to be 0. Okay, if you do not want to take 0, we can explain that also how to write down that 0 to t, that is 0, and also u at L t, that is also 0. So, we are taking our boundary conditions as 0, and we should also think that how your initial condition look like. So, we should also think that how your initial condition will look like. Just think about this. In the previous problem, when we are doing parabolic equations, only first order derivative is given in t. So, how was our initial condition? That was looking like this. Okay, this time equal to 0, this is some function f of x. But here we have second order derivative with respect to t, so you need one other condition. Let me write down that as ut, which, okay, that means derivative of u with respect to t, x and 0. Let us assume that this is some function of x which is called gx, fine. So, these are two initial conditions and this is boundary condition, and we have to simplify this problem with respect to these conditions. Now, first let me write down here about the problem, that what is this problem actually. What is uxt here? Uxt represents the displacement, of a point at a distance x, and at time t of a vibrating string, which is tied between, so we are taking which is a vibrating string which is tied between the points x is equal to 0 and x is equal to L. Okay. Then, okay, so let us read this. Uxt represent the displacement of a point at a distance x at a time t of a vibrating string. So, if you are given a vibrating string and we are taking a string and that is tied here at these 2 points, and there is some string which is vibrating here. So, this uxt gives us the displacement of a point at a distance at the time t. So, the string is vibrating, and what is the displacement of the actual string at a point? So, that is given by here u. But your string is tied at the end. So, the string is tied at the end points. So, whenever string is vibrating, there is no displacement at the end points. So, that is why this indicate our boundary condition, u0t is 0 and ult is 0, because that is tied at the end points. Okay. So, this indicate no displacement. Now, there are two initial conditions also. What does this indicate? These two initial conditions. ux0 is f of x. ux0 means when we have a initial time. So, this condition tells us the position of a point at initial time. So, when we start vibrating a string, so initially what is the position of the string when time is 0? And what is this indicate? This indicate del u by del t, which is velocity. So, this indicate that velocity of the vibrating string. What is the velocity of the vibrating string at the initial time? So, this system indicate a vibrating string which is tied at the endpoints, and it is given velocity as well as initial position. Okay. So, this is our hyperbolic equation which is solved by many methods. Okay. So, this is also solved by analytical methods and numerical methods. There is method of characteristics or finite difference method. So, we are going to deal only with the finite difference method throughout our course. So, we will deal with this and check how to find out the solution of this. Okay. So, let us start doing the solution of this. Now, what is our domain here? This is our domain here, okay, 0 to L. Okay, so, let us again divide our domain (0 to L) into m sub intervals equal sub intervals. So, this is x1, last is xm. So, what are our grid points here when we are taking uniform mesh? So, your xi is I times delta x. And what should I write down here? Value of I, your I varies from 0 to m. So, your I value is from 0 to m. Then what should I write down here? Tj. Tj is j times of delta t. Okay. So, in the time direction I am going with the grid size delta t. So, whatever time level I have to find out, I start with delta t. I have to find out the solution as t1, t2 and up to next points. Fine. So, this is the thing we have to do here. Next thing is, I will first find out here the explicit scheme. So, let us see how we will do the explicit scheme. Okay, so to find out the explicit scheme, we start with this problem here, and what we will do here, we will apply here the central difference formula. So, for that I am writing here CTCS. It means we will apply here central difference formula in time as well as we will apply here central difference formula in space. Okay, so what we will get here? Now, see, this is time variable and this is space variable. So, what I will get here in if I discretize the problem at the point xi tj, what I will get here? Let us check here this formula. Because this is derivative with respect to t. So, what can I write down from here? xi j plus 1 minus 2 ui j plus ui j minus 1 by delta t square. Because this is derivative with respect to t, so ith coordinate is s is, I am making change only in the time coordinate. So that is equal to u xx. So what I will get from here, let's in particularly for this scheme, let's take here c as 1, c constant as 1. Just for simplification I am taking here this constant to be 1. Let's see how I will find out this. This is ui plus 1 minus 2 ui plus ui minus 1, and I am taking at j divided by delta x square. So you should also write down here the truncation error, that is order of delta t square plus order of delta x square. So this is a scheme which is a second order scheme in both space and time. Further, you know how to write down this scheme. Let's simplify this scheme and write down the final version. Next time level should be in the left hand side and other levels on the other side. Let's write down this form here. Okay, so what will be the simplification here? Okay, so this is ui j plus 1, that is equal to this delta t square will go here, delta t square by delta x square is there, this term. In the previous classes, yesterday class, I was writing r as delta t by delta x square, but here I am writing this as delta t square by delta x square. Okay. So don't be confused with this notation with that notation which I was writing in the previous class. If you are you have any doubt, you can write down this as some other constant row or some other value. Okay, so this will go here, that will be r square. What can I write down here? This is r square ui plus 1j plus ui minus 1j, and further this 2 uij will I am going to combine with this one. So this is 2 minus 2 r square uij, and this term will also come here. So this is minus ui, and here we will have j minus 1. Yes. So this is our final scheme here that we can write down. Now you should also think about this, and you have to tell me that what will be the value of here I and j. Just think about this. If you want to write down in the chat box, you can write down that what will be the value of here I and j. Because value of u is given on the boundary, so I at 0 and m is already given to me. So what I should write down here, that your I is lying between 1 to m minus 1, and you can start j from greater than equal to 0. So I can take this value and further solve this value. Okay. Now let's check about this initial condition. What should I write down this initial condition? This initial condition, your time is 0. So can I write down u I 0 because t is 0. So this is same as fi. Fi means function's value at the point xi. So this is the form of this initial condition. Okay. Further, another condition is also given to us. You tell me how should I write down that initial condition. Let's think about this. What should I do with this initial condition? Okay, so I am going to write down this as equation number 1, and let's move further. I will erase this thing. Okay, so I need this value and I will erase the other things and let us check what we can write down here. Okay. Yeah. So, let us put here j is equal to 1, j is equal to 0 and see what happens here if I put j is equal to 0. So, u I 1, that will be same as r square u I plus 1 0 plus u I minus 1 0 plus 2 minus 2 r square u I 0, and last term is minus u I, and this is different. When I put here j is equal to 0, I will get here j u I minus 1. Okay. So, let me write down this as equation number 2. So, in this problem, if I have to find out further solutions and if I start with j is equal to 0, then we get the equation of this type. These values are already known to me because these are given by our initial conditions. But this value is a kind of fictitious point, ui minus 1 time level, which I am not aware about. So, how I will deal with this thing? For that, I am going to utilize this boundary condition, initial condition, and let us see how can I do that. What is this initial condition? Del u by del t at the initial time level. I can apply here central difference formula in time. Let us think about that. What can I write down here? U I central difference formula. So, that is u I 1 minus u I minus 1 divided by 2 delta t, and that is equal to g I. G I means value of g at x I. Is this fine? So, from this condition I can write down the value of u I minus 1, which is, I am taking this here, everything coming this side. So, this is u I 1 minus 2 delta t g I. Let me write down this equation number 3, where I got the value of u I minus 1, which was which value I am going to utilize in equation number 2. So, I am going to put it here. Let us check what can I get here. Okay. When I will put it here, this will become 2 time. So, what I will get here further, let me simplify the whole equation again. So, what I will get here further here? I will get here the final equation is u I 1, that is equal to r square, u I plus 1 0 plus u I minus 1 0 plus 2 minus 2 r square u I 0 minus, I will put this value here. So, this is u I 1 minus 2 delta t g I. So, we have this value here, and I am going to take this here because this is the same term, and final formula which I will get here is, so final formula I will get here is u I 1, that is equal to r square by 2 u I minus 1 plus u I plus 1 at 0 time level, and plus 1 minus r square u I 0 plus delta t and here g I, and let me write down this as equation number 4. Okay. Yeah. Okay. So, this is our final scheme here. So, if we are given any hyperbolic equation, we will have here 2 initial conditions, and so we can find out here this is our numerical scheme, and further now we get the equation, and you can see that this is explicit form because u I 1 can be find out with the help of previous time level. So, this is our explicit scheme. So, this is explicit scheme. explicit scheme for the hyperbolic equation. Fine. Okay, so next let us draw here the stencil of this problem and see how that look like. So, how that will look like? Here we have here this is here I minus 1, I plus 1, this is j minus 1, jth time level and j plus 1th time level. So, your ui j plus 1, which is this one, uij plus 1, here minus 1 time of uij plus 1 and this is minus uij minus 1, which is this minus 1 time, and ui plus 1 j r square. So, here this is r square, this is here r square, and uijs 2 minus 2 r square. So, this is the stencil of this numerical scheme, where we can write down our uij as a r square times this point, 2 minus 2 r square times this point, r square times this point and minus 1 time this point. So, this is the stencil of the scheme, with the help of which we can directly write down our solution. Okay. So, when we get this thing, similarly we can proceed further. In this next step, I am putting here j is equal to 0. So, I was getting this and I am simplifying this. Further, I can put here j is equal to 1 onwards, and definitely your right hand side is known to you. You can keep putting that, and because this scheme is your explicit scheme, and further solution we can find out with the help of this, we can find out the further solution. Okay, so let us see here. Whether we can do one example here. Okay, I think we can do here one example for hyperbolic equation, the scheme that we have done. Yeah, explicit formula already we have done. So, we will do here one example, and let us check how this numerical scheme works. Okay, so let us check this example here. So, we consider the second order wave equation, which is this problem which we have already considered. Second order derivative with respect to t, that is equal to second order derivative with respect to x, with initial conditions are given, because second order derivative in t is given. So, we have given here two initial conditions, one is u value and other is del u by del t. So, first initial condition is given to me non-homogeneous, and other one is given to be homogeneous, which is 0. Boundary conditions also we are taking to be 0. So, u 0 to t and u 1 t is given to us. Okay, so what we are given here, we have to find out value of u. So, what is given to us here? We are given here x axis as 0 to 1, and I am taking a gap of 0.2. So, this is 0.2, 0.4, 0.6 and 0.8. Okay, so, we are taking these points here. This is your x naught, next is x1, next is x2, x3, x4, and here we are given x5. So, next is t t we have to find out. So what we are taking to be here. So what is your h here or delta x here? Delta x is the step size in x direction, which is given to be 0.2, and time direction you can see here what is given in the statement. Time direction, it is given to be 0.1. So delta x is 0.2 and delta t, that is equal to 0.1. Okay, so this is the initial points that is given to us. Further, if we check this boundary conditions, so at this boundary conditions the function's value is given to be 0. So when your u is x is equal to 0 here, so the function value is given to be 0 here. On this boundary the function value is given to be 0 here, and here also your function value is given to be 0. This is 0 and this is 0. Initial condition is given to be sine pi x by 2. So here what is your x here? X is 0.2. So this will be sine pi into 0.2. We have to calculate that. So this will be that value here. Now next point 0.4, that will be half of sine 0.4 times pi. So similarly I will get every value at these points also. Fine. Now we already calculated the scheme here. For this kind of problem we have done the scheme here. What was the scheme? This was the scheme here. Okay. So we have to write down the scheme, and initial condition is also given to us. So what is gi is given to us in the problem? It is given to be 0. So gi is 0 in the given problem. So what will happen with this? Your ui minus 1 will be same as ui of 1. So I will get with this equation, because your right hand side term is 0, I will get this relation here. So to solve this numerical scheme, you will start with j greater than equal to 0. You will get this equation. Ui minus 1 I have to put with the help of this equation. Here your gi is 0, so this value will be 0, and I will get our scheme at first time level is to be this one. Now when I have to find out ui's, different ui's, that is given here in terms of initial time level. So initial time level is already given as half of sine pi x. So I know every each of these values here, ui minus 1, and because it is given half of sine pi x. So I know every value here. I will put every value here and I will find out the values of ui's at first time level. Fine. So this is the procedure we are going to follow. In the next step you will put here j is equal to 1. So you will have here ui 2, that will be is equal to r square. What is your r square here? R square is here, let me write down that value here. R square is delta t square by delta x square. So in the given problem delta t is given to be 0.01. So this is 0.01 square, and delta x is this is 0.2. So this is 0.2 square. So we have to calculate this term. I will get the value of r. I will put this value of r here, and what I will get with the help of this? I will get r square ui plus 1 1 plus ui minus 1 1, and here plus 2 minus 2r square ui, here it is 1 minus ui 0. So when I move to next time level, initially I have a difficulty because we are given this ui minus 1, which I am getting with the help of initial condition. Then for next time level our ui's at second time level are given in terms of first and 0, which we have already calculated. So there is no difficulty at all. So similarly we can start the procedure and I can go from first time level to the other time level. Okay. So this is the values at first time level. and then we can go up to second time level. So here we will have second time level. Okay, so let's move here further. Okay, so your h is 0.2, k is 0.1, and r square was k square by h square, so r is k by h. Let's put that value. I am getting it as half. And further I am writing here that your r is less than 1. That I will explain in the afternoon session, that why I am writing this r is equal to less than 1, because if your r is less than 1, only in that case your scheme is stable. So that thing we are going to prove in the afternoon class. So whatever h and k you are choosing, you have to think that you are whether r value is less than 1 or not. Okay, so here the scheme that I derived, I am putting here that value of r, which is 0.5. So we are getting value this one. Okay, so initial we are given boundary condition to be 0. So u0j and u5j's are 0, because these are our boundary conditions. Initial condition is given to be ui 0, that is equal to half of sine pi ih. Okay, so this is I from 1 to 3 up to 4. So this thing I already explained here, that how to deal with this second initial condition. I am applying here central difference formula in time, which is given to be 0, and I will get ui at -1 time level is same as ui at 1 time level. So I will substitute this value here, okay, and I will get this final scheme. So we will get here ui1 in terms of all the values at 0 time level. So we will get this value here. Further, you have to put your value of I as 1 to 5 here. So we will have here 5 equations, but we don't have to worry because this is explicit scheme. So all the 5 points I can find out with the help of the previous points. Okay, so this is our solution here. We start with j equal to 0, t is equal to 0. So this is our initial condition which is given here. You can write down here I is equal to 1 to 5. When you put here I is equal to 1 to 5, you get these initial points. 4 points I will get. Okay, we have to make a table because systematic table will give you definite idea about the solution. These are our boundary conditions, and at 1th level, when I put here different values of I in this equation, I will get here different ui's at j is equal to 1. So we are getting these values here. So actually in any equation here 3 time levels are involved. So when I am talking about j plus 1 time level, on the other side we have j and j minus 1. So when I am doing second time level, so on the other side we are calculating first time level as well as we are using the initial time level. So by using these conditions, we are going to apply this procedure again and again, and we are going to find out the solution at time level 0.5. So by applying this procedure, we are getting this solution here, this one. So here you should also observe this thing, that what's happening in the final solution. Can you see here that your system, this solution is symmetric, has a symmetric behavior, because when your x is equal to 0.2 and your x is equal to 0.8 have the same value, and your value at 0.4 and 0.6 have the same value. That you can observe carefully with the help of the value of your exact solution. So luckily we are also given the exact solution for this problem, which is uxt, which is half of sine pi x and cos pi t. Okay, so we get this thing here, and clearly you know that your sine function is symmetric. Okay, So we have this value here. So we get this approximate solution. Further, what we can do here is, just like this value is the solution at x is equal to 0.2 and t is equal to 0.5. Further, if you want more clarification, you can put these values here and you can check that what is your exact solution or exact value here. So you can compare here with the difference of your exact solution and approximated value, so that you will know that how much error you are getting. Similarly, we can do for other things. That's what we are finding here, the error, and we check what is the order of our method. Although order we are not doing here, but that we can do with the help of this table further. Okay, so this is all about here elliptic equations. So in this morning session, we have done elliptic equation, and we have done here elliptic equation 5 methods we have done, non-iterative method and iterative method. We have done 5-point formulas, one is standard and diagonal formula. Other we have done iteration formulas, which is Jacobi formula and Gauss-Seidel formula and successive over relaxation formula. So we have done a variety of questions to solve elliptic equations, in which we are doing 2 type of equations, that is either Laplace equation or Poisson equation. So that we have solved, and in the end of the lecture we have also done numerical scheme for the hyperbolic equation. So we have done only one type of hyperbolic equation, that is wave equation, that is related to the vibration of a string. So in this problem we have find out the solution, and particularly we have find out here the explicit scheme to solve this wave equation. Also we have done one numerical examples, that how we can solve the problem with the help of this explicit scheme. So in the next afternoon session we are going to do more about the hyperbolic equations. We will try to find out the other numerical schemes. Already explicit is done, we will try to find out the implicit scheme. Also we will be doing some analysis part, we will try to do stability part or convergence part, or maybe consistency of the numerical scheme. And because in the syllabus I have already mentioned that we will be doing here first 1D advection equations. So I will also try to cover advection equation and some related concepts. Okay, so that thing we are going to do in our afternoon session. So if you have any doubts up to now, you can ask me. Otherwise we are going to meet after in the afternoon session. If in the meantime you have any doubts, you can try these examples. The examples that we have already done for elliptic problems, that you can try for other values of omega. Omega we have taken in our problem is 1.1. Here it's your wish, if you want to check with other values, you can see that how many iterations are needed to solve that problem. Okay, so that is all about morning session. We will see you in the afternoon session. Till then, just have your lunch. See you after lunch.